All right, you guys, welcome back to our conversation on series and series test. So up until this point, we have talked about a test for divergence. That was the first test we talked about in 11.2, as well as geometric series in 11.2. Now, also, we have discussed the integral test. We have discussed the comparison and limit comparison test and the alternating series test. So the last test we will consider here is what we call the ratio test, and we will also look at the root test. And the ratio test is really convenient for series that have terms with factorials or terms that are exponential. So we'll see in a couple minutes as we work through an examples how nice this test, the ratio test, deals with those types of terms. Before we get to that, what we want to do is define the term absolutely convergent. So I'm going to write the definition up here, and then we're going to look at some examples and discuss the power of this definition. I want you to keep in mind this is a definition. This is not a theorem yet. We do have a theorem that we'll connect to, but this is a definition here. And our definition says that a series, so we're talking about an infinite series, and we're just looking at a generic term, right? So an infinite series is called absolutely convergent. So this is the term that we're defining. Absolutely convergent, or absolute convergence, right? So a series is absolutely convergent if the series of the absolute value of terms, so the series of absolute values, so in other words, we're going to take the absolute value of our series, I want to put a sigma there first, right? So we're going to look at the series that we're looking at up here, sum of a sub n. We're going to consider the absolute value of the terms. So if this series is convergent, then we're going to call the series itself absolutely convergent. All right, so to take a look at an example here of this definition, how we kind of test to see whether our series is absolutely convergent or not. Let's take a look at an alternating series. So let's take a look at this series. Let's do -1 to the n minus 1 over n squared as n goes from 1 to infinity. Now if we were to write the terms out here, we would get 1 over 1 squared, which is 1. And then when n is 2, I get -1 to the 1 power, which is negative 1 over 2 squared, and then we would get 1 over 3 squared, and then minus 1 over 4 squared. So we have an alternating series here. Now we definitely could use the alternating series test to test this series for convergence, and in fact we did do that in the prior video. But to illustrate the definition of what we're talking about here, I want to look at the definition again of absolute convergence. So what we're going to do here is we're going to consider, let's consider the absolute value of terms. So I keep forgetting my sigma. So let's look at the absolute value of the terms. Now if we look at the terms of the series that we wrote out, right, basically what the absolute value of the series is going to do is it's going to turn these negative terms into positive terms. So we're going to basically just end up with 1, right, plus 1 over 2 squared, plus 1 over 3 squared, so on and so forth. So what we're really looking at is the sum of just 1 over n squared. Right? So we've gotten rid of, if you will, the alternating term, -1 to the n minus 1. Now we know what the series 1 over n squared is. We know how it behaves, right? That's a p-series, which is a p-series. P is equal to 2. P is equal to 2, which is greater than 1, and is convergent. All right. Now, what we would do then in this case is call this series absolutely convergent. So I'm going to write that down. So I'm going to say, so I don't want to write with an eraser. Right? So negative 1 to the n minus 1 over n squared is absolutely convergent. Right. Now this is based on our definition, and we're going to see a theorem in a moment that says any absolutely convergent series is convergent in a regular manner, and we'll discuss why we make that connection, right, and its usefulness. I just want to illustrate this definition of absolute convergence. Now I want to do then, let's come back and let's take a look at an example where a series is not absolutely convergent. So let's take a look, and again I want to make this as simple as possible just so we can focus on the conversation. So let's look at the alternating harmonic series. Now in the prior video, right, this is the alternating harmonic series, and we had used the alternating series test, and we showed that it was convergent. So I'm just going to write that out again for our conversation. So this is convergent by the alternating series test. And again, I would tell you to go back and look in our prior video for 11.5 and see the work that we did to show that this series was convergent. So now to connect to this definition that we're talking about of absolute convergence, right, let's come back and let's consider, I'm going to run out of room on this first page, but let's consider the series of absolute values of our alternating harmonic series. Again, without writing the terms out, right, we know that this negative 1 to the n minus 1 creates the plus minus alternation, the alternating behavior. So we really are going to look at the series 1 over n is n goes from 1 to infinity, and we know this is a divergent p-series. Right? All right, so this is a divergent p-series. This is a divergent p-series because p is equal to 1, which is less than or equal to 1. Okay, so we're going to introduce another term here, another definition that we're going to say, we're going to call conditionally convergent. So I'm going to write down another definition, and this is a definition for the term conditional convergence. So I'm going to say that a series, sum of a sub n, right, we'll do a generic form, right, is called conditionally convergent. So that's the term that we're defining here. So the series is called conditionally convergent if it is convergent but not absolutely convergent. Okay. And again, we are writing these terms here, these definitions of these terms, absolute convergence and conditional convergence, because the test that we're going to consider in this section, the ratio test, as well as the root test, is testing for absolute convergence. So we'll come back to these terms in a moment when we look at those tests specifically. So we've looked at two examples here. We define the term absolute convergence. We said if the sum of the absolute value of the series is convergent, we call that series absolutely convergent. And then we've looked at an example where the absolute values of a series was divergent, but we know that that series was convergent, right? Our harmonic series, alternating harmonic series. So then we needed to come back and define this term conditionally convergent. All right, so now we have the theorem that we are going to use in our ratio and our root test. And the theorem says that if the series, so again, I'm going to speak generically, if a series a sub n, right, we have an infinite series, if this series is absolutely convergent, then it is convergent. All right, so I want to sketch out kind of the idea of the proof here and why this is true. But again, this will be the theorem that we base the ratio test and the root test off of. So the ratio and the root test are going to really be testing for absolute convergence, and we're going to utilize this theorem to say, well, since that series is absolutely convergent, then my series converges. Okay, so let's do kind of a sketch of the proof here just to show why this is true. So this isn't the most rigorous of mathematical proofs, but I want to look at the sketch of this proof just to justify again this theorem. So the first thing we're going to write down is an inequality that is true, and let's discuss why this inequality is true. All right, so we know that this inequality is true. And if I kind of cover up, in fact, let me come back and erase here for a moment. We know that the absolute value of my series is going to be positive. Right? So if I have even the alternating series, or I have negative 1 over 2 squared, when I take its absolute value, it is positive 1 over 2 squared. So we know the terms are going to be positive, greater than or equal to 0. And then if I take these terms and I multiply by 2, of course, these are going to be bigger. So writing this inequality here, we know this inequality is true for any series a sub n. Now what I can do is inside here, let me put back that term that we had. So if I add inside the terms a sub n without the absolute value, we know that these terms will be, they could equal 0, but they would definitely be positive. And they will still be less than or equal to 2 times a sub n. Right, so if the general term is positive, when I add it to the absolute value, it's going to equal 2 times a sub n. And just as a quick little example here, if I'm looking at, let's say, negative 1 over 3 squared, and I look at the absolute value of negative 1 over 3 squared, right? This guy right here, this is going to be positive 1 over 3 squared plus negative 1 over 3 squared, which is 0. So that is definitely greater than or equal to 0. And of course, it's less than or equal to 2 times the absolute value of terms, right? 1 over 3 squared. So this is definitely a true inequality, and it's also true when I have a positive term, right? So instead of this term being alternating or being negative, what if I had 1 over 4 squared, and I add to that the absolute value of 1 over 4 squared? Right, so I'm taking the absolute value of 1 over 4 squared here. So that's going to be less than or equal to 2 times 1 over 4 squared. And then, of course, this is positive. Right? So anyway, this inequality is true for any term a sub n. All right, now to finish off the sketch of this proof, what we're going to say is the following. We're going to say, since that condition is true always, if we know that the series is absolutely convergent, then by definition, right, we know that the series of absolute value of terms is convergent. Right? And that's by definition. Right? If the absolute value of terms is convergent, the series is absolutely convergent. And so if this series here, sum of absolute values, is convergent, think about the fact that this sum is a finite number. So the sum of twice that is also going to be convergent. Right? Okay, so if this infinite series of absolute value of terms, let's say, equals 5, then 2 times that, is 10. That's also a convergent series. That sum is finite. Right, so then we can use the comparison test, right? We can say, so by the comparison test, right? So by the comparison test, we know that the a sub n plus absolute value of a sub n is convergent. Right, and again, the reason for that is because we had this inequality, which we observed was always true. Okay, so again, since 2 times a sub n is a convergent series, right, the sum of 2 times a sub n is a convergent series, and this inequality is true, right, then by the comparison test, we know that a sub n plus absolute value of a sub n must also be convergent, right, by the comparison test. So if we play a fun little game with algebra, then we can say the following. So we know that a sub n, sum of a sub n plus absolute value of a sub n, right, minus the sum of absolute value of a sub n. Right? So this is in essence, right, we have a sub n plus absolute value of a sub n minus the sum of the absolute value of a sub n. We're going to get just the sum of the original series a sub n. So it's like this term here, a sub n, the absolute value of a sub n, and this sum of absolute value of a sub n, those cancel out, and I just get my original series. Right? So we know that this series here is convergent by the comparison test. We know this series here is convergent because it's absolutely convergent. Right? We know that that series was absolutely convergent. Therefore, all of this is also convergent. Right? And the reason why here, right, here's the reasoning, that since this sum, a sub n plus absolute value of a sub n, is convergent by the comparison test, let's suppose this sum is finite. It is. We know it's finite. It's convergent. So if this sum was 10, we know this sum here is also convergent. Let's suppose its sum was 5, right? So then, 10 minus 5 is 5. So if these series, so in essence, the difference of 2 convergent series is also convergent. So we know that this series, being a difference of 2 convergent series, is also convergent. So we have basically just proved the theorem that if the sum of absolute value of series is convergent, then the original series is also convergence, right? So in conclusion, basically, we would just have the wording of our original theorem. So the conclusion is that if the series of terms is convergent, then the original series, right, is also convergent. Right? So that was just a little sketch of what the proof would be to justify that theorem. So this theorem then is going to be extremely useful for us, as I've mentioned, through the ratio test and the root test. If we can show that the series we are testing is absolutely convergent, then we will be able to conclude our series that we're testing is convergent. Now, I paused the video real quick. I wanted to scroll back to our original example to just illustrate how we would use that theorem. So if we look at the series, alternating series with 1 over n squared, so we're -1 to the n minus 1 over n squared. So let's say a homework problem in this section gives us this series here and says, let me circle this in red, right? So a homework problem would give us this series and say, determine if that series converges or diverges. Now we would definitely have the option of using the alternating series test. But we've already discussed that test in detail. We're discussing the theorem that if a series is absolutely convergent, then it is convergent. So we see as an example here, we could find the absolute value of the terms of this series. And since that is a convergent p-series, and we say this convergent, then this series is absolutely convergent. And then what we would tack on to this conclusion here is, therefore, the original series is convergent. So by our theorem, since the series we're testing is absolutely convergent, then that series is convergent. Now, the next example illustrates something that we want to be careful of. If we look at the alternating harmonic series, we tested this for convergence. We tested this for absolute convergence. Now, when we took the absolute value of those terms, we found out that the series we ended up with was not absolutely convergent, right? That is a divergent series. So what we want to do is make sure that that theorem doesn't give us a conclusion if my absolute value of terms is a divergent series. right? And again, this example illustrates that in fact, the absolute value of this series being divergent did not mean my original series was also divergent. Right? We had a convergent series there. Now, there are cases where when I look at the absolute value of a series, and if that absolute value is divergent, my original series might be divergent. But there's also cases where if we take a series and we look at its absolute value and it diverges, the original series could be convergent. So if my series is conditionally convergent, right, it is not necessarily convergent or divergent. So in the end, the way that we're really going to use this definition of absolute convergence is through this theorem. That will be the most powerful piece for us here. Again, the theorem saying if a series that we're testing, we're looking at a specific series here, if we test that series for absolute convergence, then we can definitely conclude that original series is convergent. All right, so let's discuss the ratio test first, and then we'll look at the root test. And again, the ratio test is going to test for absolute convergence. And then we will use that theorem and say, since it's absolutely convergent, then this series converges. And then we'll also look at the conditional convergence piece that might come out of the ratio test. So I'm going to write down the statement of the ratio test. We're going to apply it to a couple examples and then come back and discuss specifically the results of that ratio test. All right? So the ratio test says the following. So we are testing, right? I'm going to just note here, what we are testing is any series, any infinite series we can test. Now, we might be able to test that series with the integral test, or we might be able to test it with the comparison test, or we might be able to test it with alternating series test. But what we're speaking to here is the ratio test. So I have some series, and I'm testing it with the ratio test. So there's three conditions that we could encounter here. So what we're going to do is we're going to investigate the limit of the ratio of any two adjacent terms. So we're going to take the limit as n goes to infinity. We're going to look at this ratio of any two adjacent terms as n gets larger and larger. And if that limit is existing and that limit is less than 1, then the series that we just tested is absolutely convergent. And therefore convergent. Now that last piece comes from our theorem. Okay? And we'll come back in a second and we'll kind of sketch the proof for why this works. Why, if the limit is less than 1, we can conclude absolute convergence. We'll come back to that. But first, let's talk about the second condition. So the second condition basically says if that limit is greater than 1, then the series diverges. So again, we're going to look at the ratio of any two adjacent terms in our series. That should say a sub n plus 1, right? So we're going to take the n plus first term, we're going to divide by the nth term, and we're going to look long term down the series. So as n gets larger and larger and larger, if this limit exists and is greater than 1, right, or this limit is equal to infinity, that's technically greater than 1, right? So if that limit is greater than 1 or is infinite, then the series we just tested, the series we were testing, is divergent. And again, we'll come back and discuss kind of the idea of the proof and why that is our conclusion. And then the third option is, what if that limit is equal to 1? So if that limit is equal to 1, then the test is inconclusive. The test is inconclusive. So we get no conclusion here. Now, what might happen in this scenario is that the series is divergent, Or it might be that the series is convergent. And then in that case, we are concluding it is conditionally convergent. So case 3, for using the ratio test, case 3 doesn't give us a definite conclusion. The series could be divergent. This series could be conditionally convergent. And we'll look at an example or two where we see that case happen. So let's take a look at an example here. All right, so in this example, I want to start to get a little more interesting with the series that we're testing. All right, so let's test this infinite sum of -1 to the n. And let's look at n cubed over, let's do 2 to the n. Right? So let's say n goes from 1 to infinity. Now, it doesn't really matter where n starts, because remember what we've talked about before? What we're looking is long term, right? So as n goes to infinity, how do these terms behave? That's really where the convergence or divergence is determined as this term goes infinitely many terms long, if the series goes infinitely many terms long. So my n could start at 10, n could start at 37, doesn't matter. We're looking long term here. So let's test this series for absolute convergence. And I just want to point out to you here that if I just take absolute value of these terms, so let's just say I take absolute value, like we did in the very beginning, what we end up with is n cubed over 2 to the n. And that is not a known p-series, that's not a known geometric series. So we're going to use the ratio test here. So the ratio test asks us, or requires of us, to look at the ratio of any two adjacent terms, and we're asking, what is this limit? If this limit's less than 1, we're absolutely convergent. If the limit's greater than 1, we're divergent. If the limit equals 1, we get no conclusion. So I'm going to build through this limit. Now in this particular case, right, if I look at plugging in n plus 1, so I'm looking at the n plus first term here. So I'm going to have -1 to the n plus 1. I'm going to have n plus 1 cubed over 2 to the n plus 1. So there's my n plus first term, and I'm dividing by the nth term. Oops, I don't know why I put parentheses there. So we're looking at the absolute value of the ratio of n plus 1 term divided by the nth term. We're looking long term as n goes to infinity. We're looking out far in the series. Now here's what's really cool about the ratio test, and I mentioned this earlier at the beginning of the video. The ratio test is going to work really nice when I have, exponential terms. And notice I have an exponential term, and I have a 2 to the n, which is like an exponential function. So we're going to see some really nice stuff here. Now, the first example, I'm going to kind of take some baby steps, and then in the numerator, I'm going to break up these exponential terms, right? So in the numerator, I can split up that -1 to the n plus 1 as -1 to the n times -1 to the 1. So again, multiply like bases, add exponents. I'm just going backwards there. And then I'm not going to cube this term, and I'll show you why in a second. And then the 2 to the n plus 1 term, I'm going to split it up as well. Now there's nothing I can really split up in the denominator. And what I'm going to do at this point, now I'm going to go ahead, have the absolute value of all of those terms, and let n go to infinity. So I'm going to cancel out the -1 to the n's, and then I'm going to point out that this negative sign, when I apply the absolute value there, right, that is going to go away. So -1, when I take the absolute value, it is going to go away. So I'm really just looking at n plus 1 cubed over 2 to the n times 2 to the 1, and then I'm going to flip and multiply. So I'm going to take this term in the denominator, take its reciprocal, and multiply to the numerator. Now I don't have the absolute value bars anymore. I've applied the absolute value bars. This negative term went away. And if you think about it, the term that we have left, right, the absolute value of terms, this is always positive. Because for any value of n greater than 1, 2 to the n is positive, n plus 1 cubed will be positive. So this is positive term. All right, now if we simplify this expression, notice that the 2 to the n's will cancel. So I'm going to get the 2 to the n here to cancel, the 2 to the n here to cancel. And so what I'm left with is, and now I'm running out of digital paper here, so bear with me for a second. So what I'm left with here, these terms, right, the 2 to the n's canceled, I'm left with a 1/2, so I have really n plus 1 cubed over n cubed, and the 1/2 I'm going to pull outside the limit, right? And that's really what I'm ending up with for my final step to evaluate that limit, right? Now let me leave that there for a moment. So I have 1/2, and I'm doing the limit as n goes to infinity. So notice I didn't, so remember I told you I was not going to cube this binomial n plus 1. And the reason why is this becomes much easier to evaluate without that being cubed. So since I have this quotient and the exponents are both cubes, then property of exponents says I can kind of backwards, right, divide like bases, right, create that ratio, right? So finally, what I'm looking at really, and again, I'm going to take another baby step, right? I have the limit laws that allows me to push my limit underneath the exponent. So as long as that's a fixed value, I can do that. So since this exponent here doesn't have n's attached to it, then my limit as n goes to infinity. Properties of limits allows me to push underneath. So what I end up with in this case, this expression n plus 1 over n is going to go to 1. So I end up with 1/2 times 1 cubed. And again, I've run out of digital paper here. So that whole limit turns out to be 1/2. And since that is less than 1, then this is absolutely convergent. So I'm going to say by the ratio test, the series that we just tested, which was -1 to the n cubed over 2 to the n, this series is absolutely convergent. All right, now, even though my original instruction said just test for absolute convergence, I'm going to go ahead and apply my theorem and say, and thus it is convergent. Because that's ultimately where we're going to go with this here. All right, let's take a look at another example. And obviously, I want to get a different conclusion here. So let's take a look at an example where we're going to get divergence. For this series, let's look at a series that has factorials. I want to talk about how we're going to deal with factorial terms. So let's say we have the sum of, let's say, n factorial over e to the n minus 1 as n goes from 1 to infinity. Now I'm going to use the ratio test. So let's set up the ratio test here. And again, my formula of my ratio test, right, is I take the ratio of any two arbitrary adjacent terms, and look at the limit as n goes to infinity. So I'm going to set up originally in that fractional form, and we know that we're going to flip and multiply in a moment anyway. So replacing n plus 1, and I didn't do it on that first term, right? Replacing n with n plus 1 in that entire series, and then divide by the original form of the series. Now I have all of that in absolute value and the limit as n goes to infinity. So I'm going to go ahead and flip and multiply here. So I'm going to do a little bit of cleanup, and I'm going to flip and multiply. So in the numerator, I have n plus 1 factorial, and then divide by, the plus 1 and the minus 1 cancel here, and I end up with e to the n. And then I'm going to flip and multiply. So this term goes into the numerator. And I'm going to break that up, right? That is e to the n times e to the negative 1. Because when I multiply like bases, I add exponents. And then when I flip and multiply, the n factorial goes into the denominator. Again, taking a limit as n goes to infinity. Now we notice in this case, just like in the prior example, the exponentials will cancel. So the e to the n's will cancel. And then I basically have here 1 over e. So that is constant. I'm going to pull out 1 over e. And then I'm looking at the limit of n plus 1 factorial over n factorial. Limit as n goes to infinity. Now, in the prior videos, we haven't really discussed factorials and how to manipulate them. So I want to stop for a second. I want to go on kind of a little side note. Let's have a side conversation. And then we'll come back to this limit and we'll finish off simplifying those factorials. So the definition of a factorial, let's say n factorial, is defined as being n times n minus 1, n minus 2, n minus 3, dot, 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 all the way down to 3 times 2 times 1. So in words, a factorial is defined as being the product of n and every successive integer, positive integer, or whole number, all the way down to 1. So as an example with numbers here, if we look at 5 factorial, that's 5 times 4 times 3 times 2 times 1. So we start with n, right? And then we take n, we subtract 1, here's 4. And then we take n and we subtract 2, and there's 3. Right? And then again, in our formula, we take n and subtract 3. So 5 minus 3 is 2, right? And all the way down to 1. So the way that I like to think of this again is I'm going to start with my number that's being factorial, and I'm going to multiply it by successive integers, 1 less, 1 less, 1 less, so on and so forth. Right? Now I could take out a calculator and crunch what that number is, right? And let's show how we would do that on our technology. So if I have a TI, I'm going to punch my number 5, then I'm going to hit the math key here, and then I'm going to arrow over to the probability menu, and number 4 is the factorial. So when I do 5 factorial, hit enter, it tells me that that's 120. If I'm using an online calculator like Desmos, if I have my keyboard, I'm just going to hit 5, do the exclamation point, and it tells me that that's 120. If I'm using the keyboard in Desmos here, I'm going to do 5. And the factorial is not on this keyboard, so I'm going to hit the ABC. And here's my factorial over here. So I hit the factorial, and there is 120 again. So factorials for a specific number have a specific value. Right? So this is technically 120 here. But what I want to really talk about is how do I simplify that expression that we are left with in our limit. Stop. Right? So I'm looking at this last expression here. Right? How do I evaluate this limit? So let's come back and let's look at another example or two on how to deal with that form. So what we have here is n plus 1 factorial over n factorial. So let's take a look at how we would deal with that. So I'm going to write n plus 1 factorial over n factorial, but I want to plug something in here. So let's suppose n is 4. So we have 4 plus 1 in the numerator, which is 5 factorial, and then we have 4 factorial in the denominator. Now if I write these out, all of the products, I get 5 times 4 times 3 times 2 times 1, and then in the denominator I get 4 times 3 times 2 times 1. So I don't really want to write these factorials out within the section that we're discussing, but to just discuss factorials and how we can clean them up and simplify them. In this case, the 4 factorials cancel, and I'm just left with 5. So the way that I like to think about this is if I peel off, or if I take 5 factorial and write it as 5 times 4 factorial, so I could write this as 5 times 4 factorial, because that's what it really is, right? What I just crossed was 4 factorial, and those guys cancel, if you will. The 4 factorial in the numerator and then the denominator will cancel. Now, let's suppose that I had something like n plus 2 factorial over n factorial. And again, I want to stick with some numbers here for a moment. So if I plug in n equals 4, I'm going to have 4 plus 2, which is 6 factorial, and then the 4 factorial. Now, if I start to write this factorial, let's write it out. I got 6 times 5 times 4 times 3 times 2 times 1, and then we have the 4 times 3 times 2 times 1 here. So just like in the prior example, we see the 4 factorials cancel. So, if I write this in shorthand form, 6 times 5 times, and the thing in the denominator, 4 factorial, is going to cancel with that 4 factorial. I get 6 times 5. Now, in a generic form, right, let's not plug an n value into the calculator, or excuse me, n value into our work here. If I come back to the first one we looked at, n plus 1 factorial over n factorial, right, let's look back up here. What we did was we were matching the smaller factorial because it cancels. So I pulled off the first number, and in this case it was 5, right, and then I wrote the rest in a factorial. So I could really write this as n plus 1, right? So pull off the first number and I leave the rest as a factorial because I know that those are just going to cancel off. So I'm mimicking the same process we did up on this first example. Now if I look at the n plus 2 over n factorial, I'm going to mimic the same process. So I'm going to write n plus 2 factorial over n factorial. If I come back up to this example, what we did was we peeled off the first two numbers and we let the rest be factorial because that's going to cancel that 4 factorial we had in that example. So I'm going to have the n plus 2. I'm going to have n plus 1, right, because these decrease one number every time. N plus 2, and then 1 less is n plus 1, and then 1 less is n factorial. We stop because those n factorials are going to reduce, and we end up with n plus 2 times n plus 1. So the really cool, convenient feature of the ratio test is that it allows me to deal with these factorials in a really clean, efficient manner. So just like we saw in that first example, the exponentials clean up really nice, and the factorials will clean up really nice as well. So let me scroll back up here. My Word document's going to participate with me. So in this example, I put an exponential and a factorial. So back up in our original example, original problem here, we had n factorial over e to the n minus 1. So I have a factorial and the numerator, we have an exponential and the denominator. Now in the example before this one, we had, I think this was like 2 to the n. So whatever the base is, it doesn't matter. Right? 2 to the n, 5 to the n, e to the n, pi to the n. Right? So that's an exponential form. So when we build this ratio that we have for our ratio test, we can see that when we plug in n plus 1, and then we flip and multiply, the exponentials canceled really nicely. And what I left with was a constant. In this case, 1 over e. And we're going to end up doing the same thing with the factorials. So I'm going to split this factorial up just like we did down here on this page. So what I have to finish off my limit, what I had up there was the limit of, I had the limit of, what did we have? N plus 1 factorial over n factorial. And all of that was in an absolute value. Now, if you think for a moment, right, for any value of n, like n being 1, 2, 3, 4, right, so any value of n, factorials are going to be positive anyway. 5 factorial is positive 120, so on and so forth. So I can go ahead, and apply the absolute value. It doesn't change anything. And then I'm going to peel off the first term of that factorial, right? So n plus 1 factorial I write as n plus 1 times n factorial, and those n factorials reduce out, and I'm left with the limit of, you know what, I completely dropped my 1 over e. I had a 1 over e that was out here the whole time. I had a 1 over e here. So I have 1 over e limit of n plus 1 as n goes to infinity, and this is, this is a linear function. As n goes to infinity, I get 1 over e, times infinity. So this is greater than 1, which was infinite, right, like we wrote in our original version. And so my series is divergent. And so it's not conditional, it's not absolutely convergent, right? So the series, what was our series? N factorial over e to the n minus 1. And going from 1 to infinity is divergent by the ratio test. Again, we're going to come back in a minute and we're going to discuss why this works. We'll kind of sketch a proof real quick. I don't want to spend a lot of time on that, but we'll discuss why it works. So here's two examples. One example showing how RatioTest provides a conclusion of absolute convergence, and therefore by the theorem convergence. And then here's an example where the RatioTest shows divergence. All right, let's take a look at a third example. So let's say in this example, I'm looking at the sum of, let's say, -1 to the n plus 1 over the square root of 2n. Say n goes from 1 to infinity. All right, so using the RatioTest, I'm going to write out the RatioTest again in a generic form. We're going to investigate this limit. If this limit is greater than 1, it's divergent. If this limit is less than 1, it's absolutely convergent, and thus convergent. If this limit equals 1, we have no conclusion. So I'm going to go ahead and write out the limit here. Now I'm going to start to get a little bit efficient. So my numerator is, I'm going to plug n plus 1 into every term. So I plug n plus 1 into the numerator. -1 to the n plus 1 plus 1. And then all over square root of 2 times n plus 1. Now I'm going to go ahead and just flip and multiply. So I'm going to take the denominator of a sub n, that's my original series form. I'm going to flip and multiply. So I'm going to get square root of 2n when I do that, and -1 to the n plus 1. We're taking the absolute value, looking as n goes to infinity. So I have in the numerator here -1 to the n plus 2 is what I really have. So I'm going to write that as -1 to the n times -1 squared. And then I have the square root of 2n. I'm going to deal with that in a moment. The square root of, in the denominator, 2n plus 2, because I'm going to distribute my 2 here. And then I have -1 to the n and then -1 to the 1. All an absolute value, right, as n goes to infinity. So again, we can see the -1 to the n's cancel, right? And the -1 squared is +1. And then when I take the absolute value of the -1 in the denominator, right, it just becomes +1. So I'm applying the absolute value on this step, and I end up with square root of 2n over square root of 2n plus 2. All right, so to evaluate this limit, I'm going to use a property of exponents, which allows me to take the root of 2n over 2n plus 2. And then again, I'm using a property of limits, which will allow me to push the limit under the radical. Oops, I left the 2 off on that first one. So when I look at this last limit that I wrote, 2n over 2n plus 2, I mean, technically this is infinity over infinity, and then I do L'Hopital's rule, and I get 2 over 2, which is 1. So I get the square root of 1, which is 1, and our test is inconclusive. All right, so the RatioTest doesn't provide any conclusion or any result for me. All right, now I still want to determine whether this test is, the series is convergent or divergent. So I'm going to come back and I'm going to test my original series, and we're in essence looking for conditional convergence or divergence. So what the RatioTest has done is given me no conclusion. So I'm going to come back then and let's look at the series that we had. So coming back to the original series, what do we have? -1 to the n plus 1 over the square root of 2n. So this is an alternating series. I have to use the alternating series test. So for the alternating series test, there are two conditions that we have to look at. The first one being, do the terms decrease? So is a sub n plus 1 lesser than or equal to a sub n? So for our series here, we would have 1 over 2 square root of 2 times n plus 1. Is that less than or equal to 1 over the square root of 2n? Again, this is really a question mark, right? Is this true? Excuse me, we're trying to determine that case. Right? So if I multiply both sides by the common denominator, right, what I would end up with is square root of 2n less than or equal to the square root of 2n plus 2. I think it's pretty obvious at this point. Why does that keep coming out of 1? Square root of 2n plus 2. Why?
this should be relatively obvious that this is true, right? If n equals 1, I get root 2. If n equals 1 here, I get square root of 4. Well, definitely root 2 is less than or equal to root 4, right? What I could do is I could say, if I want to continue doing algebra here, if the root of 2n is less than or equal to root of 2n plus 2, that means 2n was less than or equal to 2n plus 2. And this should be obvious. If I subtract 2n from both sides, I get to something that is definitely obvious, right? 0 is smaller than 2. So we've met that first condition. The second condition is that the terms must go to 0. Man, and I apologize for my typos here. In the symbolism of the absolute value, the alternating series test, the decreasing was the b sub n plus 1 less than or equal to b sub n. I'll come back and fix that symbolically. My apologies. So first condition is the terms decrease without the alternating term. We said yes. The second condition is that the terms go to 0. So I have limit of 1 over 2 square root of 2n. My hand and brain are not connected today. We have the square root of 2n as n goes to infinity. And this is, 1 over infinity, and that goes to 0. So we satisfy both conditions of the alternating series test. So our series alternates by the alternating series test. My series converges. Man, it's Monday, and my brain is... I didn't have enough coffee. So we've satisfied both conditions. So our series converges by the alternating series test. Now let's suppose the instruction asks determine if the series is conditionally convergent. Now what I want to do then is come back and determine if the series is conditionally convergent. Now, the definition of conditional convergence back at the beginning of the video says, if the series doesn't converge absolutely, but the series converges, then it is conditionally convergent. So we've determined that series does converge. Now our question is it absolutely convergent or not? Right? If it's not absolutely convergent, but the series is convergent, then it's conditionally convergent. Now, when we did the ratio test, we didn't get a conclusion. So what we got to do then is, let's consider the absolute value, the sum of the absolute value of the terms. So that series is just 1 over square root of 2n. All right? So we're asking, does this series converge? And for this particular example, 1 over square root of 2n is really 1 over square root of 2 times square root of n, and then 1 over root 2 is just a constant, so I'm going to pull it out, and I get square root of n. So this is really 1 over root 2, and then this is a divergent p series. So my p is 1/2, which is less than or equal to 1, which is a divergent p series. All right, p equals 1/2, which is less than 1. So in other words, we have a series that is not absolutely convergent. We just considered the series of absolute value of terms, and we found out that that series is not absolutely convergent. However, the original series is convergent, so it's conditionally convergent, right? So the series is not absolutely convergent, but since it is convergent, by the alternating series test, then our series is conditionally convergent. Okay, so we just want to make sure we pay attention to the instruction. Okay? If the instruction says just determine if it's absolutely convergent or not, I typically would apply the ratio test is what I would do. If the ratio test is inconclusive, then we're going to come back and consider the absolute value of terms, which is what we just did. Right? So if that absolute value of terms shows me that I'm not absolutely convergent, then I test the original series, in this case with the alternating series test, and we make a conclusion. All right, so let's take a look at one more example. We mentioned that this section has what we call the root test. So I'm going to come down here. Let's take a look at the root test. Now, I will tell you that the root test is quite specialized and only works in basically one specific type of scenario, and that's when we have an nth exponent. So let me write out what the root test says here. So it says the following. Let me write root test as our heading. So the root test says that if, so we're looking, we're testing, right? Let me write this out. We're testing the sum of a sub n. We're testing a infinite series. So condition 1 will say if the limit of the root of those terms, if that limit is less than 1, then the series is absolutely convergent. And our series is absolutely convergent. Case 2 would be, just like with the ratio test, if the limit of the root of terms is greater than 1 or infinity, right, then our series is divergent. And then again, similar to the ratio test, case 3 would say if the limit of the root of the terms in the series is equal to 1, then the test is inconclusive. So let's take an example here. Look at an example where we would apply the root test. Again, I want to point out to you in this example, this is quite a unique form of a series. So we're going to look at, let's say, 2 to the n plus 1 over 3n plus 2. And I have all of this to the n power. So I have 2n plus 1, 3n plus 2, as n goes from 1 to infinity. Now, we typically don't see a whole lot of series where the whole expression is raised to the n power. However, in this case, we see one. Now, to be honest with you, we could apply the ratio test here, but the ratio test, that whole limit of the ratio, algebra would just get kind of nasty. So in this case, we're going to use the root test. So we're going to take the limit. And again, the reason we're using the root test is because the entire terms of the series are raised to the nth power. You know what I'm noticing is another typo on my statement of the root test. Man, I shouldn't make videos on Monday. We're taking the nth root of the entire expression. Let me scroll back up and fix this. We're not taking a square root, we're taking an nth root. Right? So we're taking the nth root. This should be an nth root. Case 2 should be an nth root. And case 3 should be an nth root. So in our example, we're going to take the nth root of our expression. So the nth root of the nth exponent, those all cancel out, right? Those are inverse functions, and they undo each other. And I have the limit as n goes to infinity. You know, I like the L'Hopital's rule. This is infinity over infinity. So if I do L'Hopital's rule, I get derivative of the numerator and get derivative of the denominator, and the limit of a constant is the constant. So since this is less than 1, then my series converges absolutely. And then, you know, by our theorem, it is convergent, right? It converges. I had told you earlier in this video that I wanted to sketch a proof of the ratio test. So that's the last thing I want to do here, and I want this to be really quick. I don't want this to be very long-winded. Let's strive for brevity here. All right. So remember, for our ratio test, we had said along the lines of the ratio of two adjacent terms, right? If that limit is less than 1, we have convergence, right? We get convergence there, right? And if the limit is greater than 1, then we're getting divergence. Right? Now keep in mind, for a limit, let's take a look at that first case, right? For a limit, we're just basically looking at the ratio of a sub n plus 1 over a sub n. Right? We're considering that that's less than 1, right? And we're considering, for n large, right? So I'm just going to say for n large. Now, in essence, we're looking at like a geometric series here. Remember, for a geometric series, we defined R as a sub n plus 1 over a sub n. Right? One way we wrote that was, the next term was R times the prior term, right? But this was our definition for R. So in the proof, right, in our conversation of what the proof is saying, is that what we're saying is for long-term behavior of the terms of our series, it is going to start behaving like a geometric, where I have the value of R. So this is behaving like a geometric with the ratio of R, and that R is less than 1. So we know for a geometric series, we get convergence when absolute value of R is less than 1. So again, for large n, right, long term down the series, we're saying that our series is behaving like a geometric where R is less than 1, and therefore it is absolutely convergent. And when we look at case 2, we're really saying the same thing, right? We're really looking at the ratio of adjacent terms, and if that's greater than 1, we get divergence. Right, and again, we don't really care what happens for the first 5 or 10 or 20 terms. In the series, we're looking long-term behavior. So we're in essence saying that our ratio is greater than 1, right? So this behaves like a divergent geometric series. So that's basically the sketch of the proof here in this case. All right, that is everything I want to discuss with you in this video. I will see you in the next video while we have more fun with series.